my name is Elie Bursztein, and today we're going to talk about SHA-1. It has been a joint collaboration with many people. The 5 people who were helping were Mark Steven from CWI, Pierre Kapperman from INRIA, Angel Bertini, Jarek Markov, and Alex Petit-Bianco, who are also from my team. And today I'm going to tell you about how we created this SHA-1 collision. Before that, I will tell you a little bit about the story about how you do cryptanalysis and break hash function, and then we'll talk about what happened in the post-collision world. We had a little bit of problem with the calibration of the video projector, so I tried to shrink down a little bit the slide. Everyone can see them correctly? Yes? All right, awesome. So let's get started. To make sure everyone is on the same page, let me briefly recap what a hash function is. A hash function, or a cryptographic hash function, has 2 unique properties. The first thing is when you have 2 files, if they are different, they should hash to a different digest or short hashes. So basically, a short hash is a fixed string which compress your arbitrary long file into this unique identifier. And people use that as a unique identifier for files. The other thing that is obvious for many of you is that a hash function is one way. You can hash the thing, but you cannot go back, and you cannot learn anything from the file by just looking at the hash. These are the 2 main properties of a hash function, and a lot of people depend on it. For example, hash functions are used or involved in documents and software signing. You can use them, for example, for Windows update, Firefox update, and so forth. They are used to make sure we can verify the signature. They are also used in the same way for HTTPS certificate. They are involved into helping ensuring that the SSL certificates are signed by a CA authority and are therefore valid. They are used in version control, and you will see that play a huge role in our talk. And finally, they are also used in backup integrity to check which file has been backed up and if the file has been backed up correctly. They are also used in a slew of other software, including databases, some file system, and so forth. And this is this huge and variety of software which make it very hard to understand all the consequences of what happened when you use a collision. I'll give you an example later in the talk about unforeseen consequences when you try to play with collision. So, what we're going to talk about today. We're going to talk about 3 things. First, as I said, we're going to look at how we're going to attack hash function. Then we're going to discuss how we found the hash function, the collision, and what happened and what not. And finally, we'll discuss post-collision world, and more specifically, how you deal with legacy software. We still use SHA-1, and how you do, what is the future hold for hash function, where we're going to. So, before getting started, the one thing it's very important to mention is SHA-1 collision is just the final straw of a very, very long line of research, and we are standing on the shoulder of giants. Among all the people who contributed, and there is a lot of people who did over the last 15 years, 2 stand as giants, and they are not me. They are Wang, who was the first one who in 2005 came up with a theoretical way to attack both MD5 and SHA-1. She's the one who divided the method that has been refined and finally led to the collision. The second one is my co-author, Mark Steven, who for the last 10 years actually was the one who kept going at it, and despite other people dropping out, decided to hold strong and basically carry out all the work till the end. So they are the 2 who deserve most of the credit for the work. I was just lucky to be there and be able to give them a helpful hand. Actually, a fun anecdote is, that was my second attempt at SHA-1. When I was at Stanford back in 2009, 2010, we looked briefly at the idea of trying to help to break SHA-1, and we looked at it and we were like, no way, that's way too complicated, it's too much resource intensive, can't do it, and we gave up. And I think a lot of people did give up as well, because it seemed, except to Mark, an impossible task. So I'm glad we were able, as Google, to help providing the resources. So if you take something from the talk, is like Mark Steven is the awesome guy, and Wang was the genius behind the theoretical attack who get all started. So attacking hash function. There is quite a few confusion about what are the different types of attack are, so I'm going to sum them up. But before that, a quick show of hand. How many of you know what a collision attack is? Quite a few, okay. How many of you know what is a pre-image attack? Well, less people, right? Okay. How about the second pre-image attack? Okay. So to make sure we're all on the same page, we're going to briefly recap. You'll see it's a bunch of few diagrams. It's going to be very quick. So a collision attack, and that's the topic of today, is basically the attacker have 2 files in control, And the goal is you create two files who hash to the same thing. So basically you are violating, as I said, the early principle that two files should hash to a different hash function. That is a collision attack. We have also another type of attack, which is called pre-image attack. In that case, there is an unknown file, and you know the hash, and the goal as an attacker is to be able to engineer a second file which will hash to the same thing. The second pre-image attack, which is the one which is confusing most people, is where you know a file, let's say your SSL certificate, and as an attacker, you create a file which is a doppelganger in the sense that it actually has the same hash. So far, so good? Yes? Awesome. Okay, so how do you create a collision attack? That's the one where basically we have a lot of practical results. Pre-image and second pre-image don't have practical attack for the main hash functions such as SHA-1, but also MD5, and of course the newer one like SHA-256. So we're going to focus on the collision attack, which we can do in practice. So collision attack are not brute force attack. That's the first thing which is important to understand. You cannot brute force your way out of creating a collision. It's impractical. Even if you were to use GPU, and even if you were to use a ton of GPU, you can't. To give you an idea, we think it's about 12 million years of computation with a GPU to get to a collision. Not going to happen. So if you can't do that, what are you going to do? You are going to use something which is called cryptanalysis. And the idea of cryptanalysis is we are studying how the function diffuse the bits and how they scramble them in a way to find biases that we can exploit to reduce the size of the computation to a point where we can finally do it. So I'm going to give you a primer on cryptanalysis. I'm going to skip a ton of detail. It's just for you to get an idea. If you want more detail, research paper, not me. All right, so here is a view of, we're missing a slide here. Okay. Okay, we're missing a slide, that's fine. Okay, so here is the unrolled version of the SHA-1 compressed function. So the SHA-1 compressed function is not the one you're going to find on Wikipedia. If you go to the Wikipedia page, you get a more simpler function. The reason why we use this representation is because when we do cryptanalysis, we need to understand very precisely each of the steps of the function. This is what happens when you have a block. So you chop up your file into small block and you hash them and then you pass it to the next and to the next using something called a Damgar-Merkle construction. So basically, it's a function who does the scrambling, right? And we study it. It's 80 steps long, and you see them on the screen, or at least a representation of them. And we do study how the bit flows through the thing. And the thing which provides the scrambling are these little purple box, like f is a nonlinear function, plus is a 32-bit modulo operation, and so forth. So how cryptanalysis works? The idea is we are studying message differential paths. So the idea is we try to understand for a group of messages how the bits are moving and how they are being swapped around or flipped and so forth, and that's the red dot you see on the screen. So when we have this understanding, that gives rise to what we call a equation system, and for SHA-1 we know exactly what happened for the first 16 steps. Remember, there's 80 of those, so for the first 16 it's basically solved and we understand what happened. So we can understand how to reduce the computation. Now we have reduced the computation by 16 steps. Then we use a bunch of tricks, including boomerang, neutral bit, and so forth, which is basically try to counteract the chaos and the entropy creeping up to the point of pushing the computation to a smaller part by another 8 steps, which is up to step 24. And then, well, we don't know. And that's the part where you need this huge computation. That's the intuition, at least, where this is the part from 24 to 80, where we have we cannot really understand what happened, and it's too big. The state explosion is too large, so we cannot. That's why we use a GPU to actually compute all the possibility, or a huge fraction of those, because we cannot understand what happened there. So how do you create a collision? Well, we use the idea from Wang, which is the idea of using two blocks. So you have a bunch of the beginning of the file, which we call the prefix, and this is whatever you want. And then we have a first block, which we call a near collision. So what is a near collision? A near collision is two blocks, which basically are very close to each other for a definition of closeness. So basically imagine that those two are a good candidate, and they are different, but they are sufficiently close that we have a good guess, or we have a good belief that they're going to be resolved with a second block. So basically we take the input of those two blocks, and then we have the second block who basically cancel out those two collisions, and then you end up with the same output. So at that point, the left and the right will have exactly the same output, and after that, you can put whatever you want after that, because the collision has been resolved. That is the basic idea of a collision, and the non-intuitive part is we use toBlock. All you have to really remember is we have a prefix, which is basically something you have to choose in advance. Then you have the near collision, and then after that, it's all the same. From a perspective, it's all the same because there is no dependency in how you create a hash function to the past. So at that point, it's identical, and you can put whatever you want for the suffix. So, okay, so I'm going to skip this one. This was the one before. Not sure what happened. So how do you exploit collision? So exploiting collision. The one we did for SHA-1 is what we call the fixed prefix attack, which means we had to create a prefix, so choose a green box before doing the computation because we can't change it afterward because it feeds into the collision. So we selected the prefix, and you have to select it in a very smart way. And then we have the collision blocks, and after that, you can do what we call an arbitrary suffix, which is you can jam whatever you want after that, and you can create many, many documents which have a collision in it, and we'll show you how we can exploit that in a minute. So here's how it works. So it doesn't seem very powerful, right? Because you're like, well, you have to choose everything, and everything is pre-computed. That is true, but the prefix you choose will actually influence how much you can do. In our cases, we use PDF and JPEG. You can think of other stuff like ES, like other type of file format which have flexibility, but PDF for us was the best one. And so the idea is we use a collision block to change the length of specific fields, such as comment, and that way what we display on the screen will be different from file 1 because it's going to point to one part of the suffix, and on the other file, it's going to point to another part of the suffix. And that way, even though we have the same suffix, we are able to display different view of the world because the collision blocks themselves are used to control some of the display function. I'll show you a practical example later on in the talk. All right, chosen prefix attack. So that was the one which was used in MD5. This is for reference. MD5 is way more weaker, so in that specific case, you don't have to worry about choosing a specific prefix. You can use the one you want. And that gives you way more flexibility. I'm going to show you a practical attack that was using the MD5 attacks just to illustrate the purpose. All right, enough theory. Now we're going to go to the real-world attack, and I'm going to show you exactly how to use those things in practice. And we're going to start with MD5 because that's the one which happened about 8 years ago, and so we have a lot of hindsight to look at and a lot of real attack to show you. SHA-1 is too new to have those kind of stuff. It gives you a sense of what you can do when you have those collisions in real. So in the first attack which was created using the MD5 collision in practice was creating a rogue SSL certificate. If you're able to manipulate the signature of a certificate, it turned out you can create a self-signing certificate for everything you want, which is valid, and you can impersonate any website on the planet. This is what Mark did with Alex Sorotorov and a bunch of other people back in 2009. And so the way it works is as follows. This is what an SSL certificate looks like. You have a bunch of fields which are the serial number and the validity period, which are which I give you by the registrar, and then you have the real cert name, which is basically which domain is your certificate signing for. And then below that, you have something very important, which is the X509 extension CA false. What it means is your certificate cannot be used to sign other certificates because obviously you're not a CA. So the whole goal when you forge a certificate is to swap those two fields. So how you do that with a collision, here's how you do it. First, you write the cert name to say, well, I want to be able to sign for everything. So I remove the real domain name and I put a star instead. Then I put my own public key, obviously, so I can actually do the creation. And then I say, well, I'm a CA certificate, right? And then after that, you have to hide the real public key. And you do that by hiding it into what we call the Netscape comment extension. So a lot of SSL certificates have a lot of fields, and one of them is the ability to jam comments in it, and you can use that as a neat trick to hide the previous public key, and you use this space to create a collision. Then you leave the signature, you copy-paste it to your brand new fake certificate, and you have a signing certificate. That's basically how you create a fake valid SSL certificate. If you think that's a academic attack, it's not. It turns out that in 2012, a malware was discovered which was mainly spying on an Iranian computer. The malware was called Flame. I don't know if you remember it. This malware was fairly unique in the sense that it was using a colliding certificate to push fake Windows update. What happened is someone well-funded decided to create a collision by lifting the signature of a Windows terminal server, which should not have, and removing the restrictions. Those very old certificates were only used for compatibility, and they had a bunch of restrictions. So what they did is they took the certificate, changed the CNAME, and then removed, say it's only for Windows XP. They say no, it's for everything. Repackaged it and used it to deliver malware as a form of Windows update, which we're saying was a certificate to attack Iranian computer. What's very interesting about this attack is because it used collision, Mark and his team was able to reverse engineer how this malware works, and were able to figure out how the collision was created. And lo and behold, it didn't use any of the technique which were discussed in academia in 2009. It was using a completely other technique, which were using a 4-block collision. If you remember, I told you the 2-block collision is the way we do it because it's the most efficient. So now that the people who created the Flame fake certificate was not using 2 blocks. They were using 4 blocks, which is less efficient. You can still do it. And were using vector, which were not the one discussed in academia. So someone in the world had enough cryptographic knowledge and enough resources to pull out this kind of attack, which led a lot of people to hypothesize it was a state-sponsored malware. And that's the explanation behind this. If you want to know more about it, there is a very, very neat paper by Mark, which is called Reverse Engineering of the Cryptanalytic Attack Using Flame to Super Malware, which explains all of this in detail, but that's the bottom line. So basically, you can weaponize collision to create attack, and it has been done in the past, and that's why taking collision seriously is so important. So where do we live today? Well, for the old functions, they're all dead. MD4 is dead for a very, very long time. MD5 is so dead that you can do it on your smartphone. No kidding, you can literally create a collision in your smartphone. And then SHA1 is a new attack we created, and it took us 2 to the 63 computation, which is pushing the limit of what we can do. It's one of the largest computation in the world as far as we know. So how did we find this collision? Well, we started in 2015, and as I said, the prefix has to be fixed for SHA1, so we had to create a clever prefix. Ange Albertini was the one who looked at this because he is very, very well known for how to do world expert into crafting interesting documents. And so he came up with the idea of using PDF and JPEG, so we can actually have a prefix which gives us malleability to show one image or another and make it very, very easy. I'll show you a demo in a minute. And then I ran the first computation between 2015 and 2016. It took me about 9 months and 300,000 computer. Then excitement began. We reported the result, and then we had to develop the full attack, and we had quite a few sweat there. I'll tell you that in a minute as well. And finally, we did the second large computation early 2017, and then we issued the release in the press in February 2017. So what Ange came up with to be able to use the collision to its full extent was to embed a JPEG into a PDF header. So we'll create collision, which will be like valid PDF document. And the trick is JPEG has something called a comment. And the idea is you will use a collision as a boundary for the length of the comment. So both files, while having the same hash, will actually display different things, because in one case, the length will point to the first image. In the other case, by rebounding on comment of comment, will rebound to another images. So while the content of the two files is the same, if someone is to open it, you will see 2 different images. That's the power of creating collision. And of course, you can use whichever images you would like. So now you can create any pair of doppelganger files. So try to imagine 2 insurance contracts. One say you only have to pay $1,000, and the other one say, well, no, actually you have to pay $1 million, and those would hash the same thing. That's the kind of stuff you can do with that. So then I took Mark's code and tried to scale it up to, as I said, to use about 300,000 core in multiple data centers around the world. And most of the complexity was to find the right balance between resilience and performances. So every time you have to dispatch a new job, we have to copy stuff in memory, move things between computer and so forth, so there is a lot of overhead. So you want to run as long as possible. At the same time, computer failed, and we have to reboot the job, or the job had been preempted and so forth. So we settled on after a few trying out about 1 hour batch, and we run, well, quite a few of those, like millions of those. And then I also refactor the code to be stateless. One of the difficult things when you do this large computation is when you have a database where you have to pull all the jobs. Instead of doing that, we were making each job stateless so you can restore them, and then we were using basically a random generator to decide which SHA to do instead of having a synchronization, because otherwise you have to deal with failover and replication of the master and become a bigger hell to manage. And last but not least, I make a huge mistake. MapReduce is a very famous computation framework, and the idea is you map your computation and you're going to reduce to all the solution. I'm like, that's perfect. That seems to be the great tool to do the job. So now it's absolutely the wrong tool for the job, because a map is very, very complex. You explore the entire space, but reducing is the part where you aggregate all the solution is very small. It's only a few bytes. And so we were spending a lot of time waiting for the last part of the computation to finish. I was running batches of I think 50,000 jobs at the time, so 15,000 hours by 50,000 hours. And so as you can see on the graph, half of the time of the job was used for basically waiting for the last bits to finish. So for the second computation part, we actually moved away from this paradigm to using a simple job system where we have a factory and a bunch of jobs and make them all independent, which was way more efficient. So lesson learned, don't use MapReduce for this job. We learned that the hard way. Then becomes the part where was the most scary. We finished the first computation sometime in, I believe, January, and then in the middle of the night, my phone rang, and then I know we found the first collision, really excited. I sent an email to Mark and said, hey, we found it. Great, okay. And then he started to look at it. I'm like, can we get to it? Can we get to it? And I'm like, wait. Looking at it. And then turned out that at first glance, what we found was not solvable, which means that we didn't know how, we got an equation system to find the second block, but we couldn't figure out what was the equation system had no solution. And then we were very, very scared for quite a bit of time that we couldn't do it. But then Mark and Pierre figured out how to add extra condition and fix the solvability using SAT techniques to actually make it work again. And then we were able to find more speed up to accelerate the computation, and then we were able to run the computation, and then Yarek from my team actually ran the second stage of the computation through GPU. So GPU is very interesting. A lot of people say GPU is great for crypto. That's true, except the architecture is fundamentally different from a CPU, so you have to rethink how you do things. In particular, memory transfer is very expensive, so we couldn't do load, unload, and those kind of stuff. You have to allocate memory, do your computation, allocate memory, and so forth. So what we started to do, and that's Pierre's idea, is to use a feed-forward, where we compute the base solution in CPU, and then we move on to the first few steps between 14 and 26, and we compute a ton of potential solution, use the GPU to compute all the next step, and until we have exostatic, do one step, and move one step, move one step. When we don't have enough solution, go back and forth. The reason why that works is because the first few steps, you have very, very little solution. This is a graph in logarithm, logarithmic scale, right? So it means that the first step you do maybe 100,000 computation. The one in the middle, you have up to 100 trillions of solution. So it quickly ramps up. So what we do is we were saturating the memory with as many potential next steps, do all of them at once, and if we don't find a solution, backtrack, generate more solution, move back and forth, and so forth. So it's a completely different way to approach cryptography. So while GPU is great for crypto, it also requires a lot of new way of distributing, scheduling your computation, because you don't have the same memory and general memory manipulation as you have in CPU. All right. And then we spent 110 years of GPU, a far cry from the 12 millions we would have spent if we were using brute force, so we succeeded. That being said, before we succeeded, we had a funny incident. I mean, I didn't find it funny at that time, but now it's okay. So Yarrick finished the computation and for my team and sent an email to Mark saying, hey, we found the collision and we are ready to celebrate. You know, the champagne is there for a few weeks. We're like, well, we're going to celebrate. It's going to be awesome. And Mark said, doesn't work. And we're like, what? Doesn't work. What do you mean it doesn't work? And like, doesn't work. And it turns out because the way we did the computation, we had it done in big Indian instead of little Indian, and he was looking at it the other way. Yeah. So we fixed it. It was fine. It was like a one-line change, and then it was all fine. But I'm telling you, we were white. It's like. Anyway, so. And then we were happy, we were able to create those colliding PDF. You might have found them online. So basically you have the same SHA-1 and the different SHA-256. And as you see, because we use a comment of comment trick, one is blue, the other one is red. That's the idea we had. And then we were like, okay, we're going to give the world 90 days before we release the code to create two PDF which are doppelganger. Well, trust the internet to do it in 2 days. So they have a better tool than ours. So here the link below is the GitHub one. So I'm using their tool. Thank you for recreating it. And so basically that's easy as is. So we have two PDF which have different value, a cat and a tiger. And that's what you do is you basically use a collider script. And the collider script will basically merge both of them into one PDF and align the comments from one point to another. And that's how fast it is. That's like literally real time. And then as you can see, boom, you have two PDFs which have the same. Thank you. Okay. And then you have the SHA-256. All right. So here is the gig version behind the scene. You have the fixed part, as I promised you, which says the PDF headers, and then below it we have the JPEG start, and you see, and then following that we have the JPEG comment. And then at the border of the JPEG comment we have our collision block, right? And you can see it here. Let me try to do this. You see it here, right? You have the last bit of the comment which is inside the collision block. So they would be different in both cases, right? And so one of the comments is 173, the other one is 17F. So as a result, you do create a desynchronization, and in one of the file, the image starts way lower, and it's a comment. In the other file, well, so in one case I say it's a JPEG, and then in the other case it's a real image. And that's how it works, right? So a lot of people were confused when we showed the attack how we can do and create as many as we want. Try to explain that to the press. So like, and then that's what it is. I want to also give a big prop to Hector Martin, which is a guy who actually created the visualization. Again, I had a great one, and then he did a way better one, so I'm stalled with his permission, his version, because I think that's a clearer version we have. So thank you for him to do that. So post-collision world. So what happened when you create a collision? First thing, and that's the thing which actually was the goal, we released a collision a few days, or I think even on the day of a meeting between browser, which is a consortium to decide what is the future of a web browser, and there was about to have discussion about prolonging the lifetime of SHA-1, except it was supposed to be sunset, but people were like, no, we might extend it because some people have complained. But in the light of the attack, Firefox finally gave up and said, fine, we're going to immediately, ahead of schedule, stop it, which was exactly our intention. If we engage into doing such a long computation, it's not for the fun. Also, it was very fun. It was because we really wanted to push the world to stop using SHA-1 once and for all, and as many of the cryptographic loom, unless you really show the money to people and the real attacks, they tend to delay it for another year, right? You know, out of the sight, out of the mind. So we decided to put it in front of you, so you have to do it. And I think for us, that was the most important thing: is we deprecated SHA-1, and as a result, users we feel are safer. So that's really the goal of the entire exercise, and it was a well worth investment. Microsoft did the same in May. So now I believe every browser have deprecated SHA-1, so now we are in a better place. We got leaked. Someone put a bet that SHA-1 will be broken in 2017, literally mere hour before we were about to release. I have no idea who it is, but the guy made 8 Bitcoin, and I want my share. So also I saw Mark, so the release was about 5 a.m. PST because he's in Netherlands, and so I saw him a few hours before scrambling to try to get the bug bounty for Bitcoin. So there is these people who are giving a little bit of Bitcoin money for the people who break SHA-1 to incentivize them to do, and I was seeing him rustling to get the money, but he did. So he did claim the bounty just in time, so Mark got the bounty, that's fair. Hopefully no one stole it from us. And then I spoke about unforeseen situation, right? And I think the most impressive one and completely take us aback was we knew Git had problem, and I'm going to talk about it in a minute, but we didn't thought of SVN because none of us used SVN for a very long time, so we didn't thought of it. But then a guy from WebKit was like, WebKit, which is the web renderer for Safari, one of the engineers were like, oh, we use SHA-1, let me make sure we don't are vulnerable for collision, which is a great idea. And so he pushed his unit test to the SVN of WebKit, and the WebKit SVN died. It's not like you can revert, it just died. And for 8 hours, you see all the WebKit engineers completely freaking out, like, did you try this command? Can we do this? And ultimately, they were able to recover it, but it literally destroys the entire SVN for WebKit for 8 hours. And then Apache did issue an SVN emergency patch and say, please do not test collision on the SVN. We know it's broken. Don't do this. So that's an unforeseen collision. That's an unforeseen situation. If we had known, we have given advance notice, but we didn't. We didn't have the test vectors. We didn't know it would break anything. But we broke Git, which means there are other software somewhere which are broken by SHA-1. So you have to find a way to mitigate those, and that's going to be the next part of the talk, which is what do you do when you think there is a SHA-1 software looming into your network, right? What do you do? Well, we have a great example, Git. So despite the early warning, and there was a long thread, and I put a link there, and they're on the slide, about people trying to warn Linus Torvald to not use SHA-1. They're like, no, that's fine, I'm going to use SHA-1. Don't do it. No, that's fine, I'm going to do it. So at the end of the day, Git used SHA-1, and it's baked in so many assumptions that it's really hard for them to move away from SHA-1. They are moving away from it finally, but it took a lot of discussion, and it's still not there. So now we have a very well-used software. How many of you use Git? Yeah. So all of you use something which is vulnerable to theoretically to SHA-1 collision, where we can have 2 blobs which have the same collision, and you end up with two different views of the world for the same Git repository. Not good, right? So how do you mitigate that? Well, turns out we have a tool. And actually, Mark invented this tool. He invented this tool and then applied it, as I said, to Flame. It also works for SHA-1. The idea is to use counter-cryptanalysis. It's a very mouthful word, but the idea is because the way you create collision create unique property into the file. Most likely there are trivial differences due to the way we use differential paths. You can, with a single file, detect if this file is part of a collision. It is very, very high precision. It's like the false positive are 0.00000, like 1701. So you can run it in a production system. It has a little bit of overhead, but it's okay. And it's also allows you, which is very cool, to understand if you see a collision, how it has been constructed. So you know if it's ours or if it's a new one we've never seen. So that's how they did reconstruct the Flame one. So counter-cryptanalysis, Mark improved the version he had and pushed it on GitHub. So if you have a SHA-1 software, using SHA-1, please use counter-cryptanalysis. We do. And we did that. So someone from Google, Sean Pierce, fixed Git to basically do counter-cryptanalysis check when you submit. So Git will refuse any collision blob. The other one who did the same thing is GitHub. GitHub in March announced in their blog, they're like, well, fine, we're going to use counter-cryptanalysis. So if you use GitHub, how many of you do use GitHub? That's it? No, I'm kidding. A lot of people use it, right? You are protected as well because they did put in place a check when you push your commit to actually do this. So the way you actually deal with legacy software is by doing detection and proactive mitigation. And even Git got onto the counter-cryptanalysis bandwagon. Actually, it was deployed in 2.12.2, so now we have this thing. We have counter-cryptanalysis also for every Gmail document and every Drive document who goes to our system. Some of our users did test on the day of the release to see if it was working as internet. It does. The reason why we do that is because we are concerned about people using old client software that we don't know of. They might actually store them in backup software we don't know of. We have a lot of corporate users as well, so we don't know what their backup systems are. So we basically prevent collisions that way, and you can do the same. As I said, we are concerned that crashed legacy software, like SVN, might have colliding documents with different terms like contract, lease, power of attorney, and so forth. And of course, black swan, which is unforeseen consequences that we don't know of, and we really don't want to know of. And so how much does it cost us? About 4.5% of extra computation for every email attachment that we scan that way. That's based on the 1 billion data set we tested after we released it, so we believe that's a well worth investment. It's not a huge number. It's significant, it's not like impossible to do. So where does it leave us, right? Well, the future is bright. It's awesome. We have a lot of new hash functions coming online. We have SHA-256 and the SHA-2 family, and we also have SHA-3 and Blake. And what's great about all of them is they are using different construction, which means that if one breaks, it's unlikely it's going to break all of them at the same time, so we have a lot of diversity to choose from. They all have different perspectives, so we are in a very good place. So hopefully you won't have that kind of talk for the next 10 years, hopefully. Yeah, so takeaway, SHA-1 is finally dead. Long live to SHA-256. Counter-cryptanalysis is a really cool tool, and I hope I inspire you to check it out. And the future is good. So thank you very much. I'm going to take any question you would have. Thank you very much.